Hey, John here. Just like any other programming language and environment, Verilog requires that you get things just right or it ain't going to work. So before you get your stuff going in an FPGA, you want to be able to test it and verify that everything's just right. And to do that, what I like to do is simulate what's going to happen in the FPGA. And I've got a bunch of little demo apps here that we can look at today to figure out different ways of figuring out what our application's doing, printing out the output and plotting it and whatever other features that Verilog has to offer to help us out. As always, one big thank you to all my Patreons, especially the VIPs. Follow the link below in the description on YouTube if you want to join the Patreon club. I really appreciate it. Thank you very much. Simulation. Verilog simulation. Okay. So in this repo here, Verilog examples, this is going to probably start up filling up with a lot of the example code that you see on this this series on Verilog. I'll just keep adding them in here as we go, okay? So don't be surprised if this gets much bigger a couple of weeks from now if you're joining already in progress. Okay, simulation 1 through 6. Here's a directory. My window's wrong. Let me fix that. There we go. Here's a directory where I've cloned this repo. So let's go and see what's going on. You've seen this repo before if you watch this series. A link below to a playlist on YouTube if you joining in the middle. So these simulation directories don't have pin configs. They're not targeting any particular board or anything. These are generic Verilog test bench programs, or they are what will become test benches, and that's why we're doing this, by the way. I want to make sure that we all understand Verilog well enough that we can differentiate between what we call simulation and the synthesizable subset of the language, because the synthesizable subset of the features represent those that can run in an FPGA. These things, the superset of all the features in Verilog, I won't talk about every one, but I'll talk about enough so that we can use Verilog to test our Verilog, which is kind of cool, all right? So each one of these little sim directories has a README file, and in here, to remind me why I made each one, okay? So what's going on here? The first one, Verilog simulation timing. Why do the values of things actually change during simulation? I said that. Or when do the value of things actually change? And I was struggling with this particular word right here. Things is a... Be careful what you call things in a Verilog program. This is almost isn't a program. I don't even know what to call it. It's a circuit. Remember, we're doing this because we want to model an actual circuit. This isn't, writing Java or C++ or C# or Python or whatever that. No, it doesn't work that way. What we're doing is we're describing a schematic. And what happens in an actual circuit that's built using said schematic is that everything in the circuit is running all the time. So when we write 2 lines of code, we have to ask ourselves, do these 2 lines of code represent 2 different concepts that happen in order? Or do these 2 lines of code represent like 2 components in a schematic where both of them are doing something all the time at the same time? Potentially different things, in fact. Okay? So let's keep all that in mind while we move forward on Verilog in general, because the biggest difficult thing that I had when I was learning Verilog was getting a grasp on 2 things. One, differentiating between synthesizable code and non-synthesizable code. Non-synthesizable meaning things that we write so that we can simulate something, but we have no intention to ever put that in the FPGA itself. When I started, the documentation was just a morass of not really pointing out the difference. So I was incredibly disoriented. So I'll probably way overemphasize the difference for you, even though today it may not be so difficult to differentiate with all the doc and all, all the years. A lot more people have gotten into this, but I just remember how hard it was for me to get started. So I'm trying to knock off what I consider to be the worst things. So there was that. And the other thing was trying to get a grasp around when I simulate something in Verilog, what really happens in what order? Because Verilog is about reproducible designs, and order matters in there, and order does matter to Verilog when it matters to Verilog. So there are times when it does, times when it does not. So today, what we're going to do is we're going to learn a little bit about how to just make this thing go. What are all these weird things that we've seen in the programs that I've demonstrated as little kind of when trying to just download Blinky apps and stuff to some test boards that you've seen in the series so far, okay? Try to understand what all those goofy things are you might not have seen before. And also point out a few things where things you do recognize and may have seen before don't necessarily work the way you might think. So, all right, starting at the beginning, Sim 1 here. First of all, what happens here is because there's no real hardware, these are meant to only run in simulation, interactively or not really interactively in batch. The make file doesn't have any way to, I suppose I should remove this program entry here, but what we're going to do is I added a rule here that just runs the simulation, but doesn't bother to open up the plotting tool. You've seen that before. That's this rule down here, okay? I'm going to go ahead and fix this while we're in the neighborhood. It's possible that I might have left a couple of these still in here with programming in there. I don't even think we need this, but I'm not going to mess that up. I'm not going to call that as an audible right now. The way this works is it's the minimum. All we're going to do is we're going to use iVerilog to compile it. We're going to use VVP to run it. Okay? Now, you're going to see when I run my example simulation programs, we're going to print things out. Now, so that should be a huge clue there that this will never run on an FPGA because FPGAs don't have a screen on them. So let's jump to the printing part and then go through this one line at a time here. See this dollar display? The dollar things like this are either system functions or system tasks. And we'll differentiate more on the difference between the two at a later time, but the short of it is these things are like library functions that are provided by Verilog, and display just prints this stuff out. It's not unlike the printf in a C program where we say, dollar this, dollar that, or rather said percent this, percent that, and so on to format a string using this template and these variables over here. Dollar time is also one of these system provided things. This is pretty important. That's the clock that ticks as the simulation runs. So let's go back to the top of the file and go one at a time, starting with the time scale, which describes that clock that ticks. Okay. Things that start with a backwards quote are like compiler directives and system directives kind of thing. So this basically says I want to define the time scale that the simulation will use. Here's the resolution of the clock. And this here is the amount of time, as they say up here, that's represented by #1 in the code. And those are delays. Verilog calls it timing control. So if I put a #1 like right here in my code, what will happen is this will happen. And then 1 unit of time that we just saw defined above will wait for that time to pass. Then it will do what's happening down here. Okay? So we'll come back to that in a minute. So how do we know how much time that is? It's what we declare up here. So what I'm doing is I'm saying I want the log file. We talked about this before, this VCD, what's called the value change dump file, okay? Everything that writes into there, I want it to be stored in units of 1 nanoseconds per, of resolution. Okay, so every time we print out the time, it'll be expressed in nanoseconds. Every time I say pound 1, I'll waste 10 nanoseconds of time before moving on to the next one. You can put whatever you want in here up to seconds and down to like picoseconds, okay? So this is relatively slow, all things considered. In simulation, it doesn't, we are not simulating propagation delays and things like that. So even if this is a picosecond / 1 picosecond, you'd get the same results, okay? There are ways to model propagation delays, and then changing these times would have an impact. We're never going to get there. I'll leave that as a task for the student, okay? Honestly, I'm not sure that Icarus does that. Correct me in the comments below. Somebody give me a pointer to it. As I think it would be neat to do, I just don't know how to do it. Never tried. Okay. What's next? As we'll see, variables that are used without being declared anywhere, without being defined anywhere, I should say, in Verilog default to a type wire. That's very annoying. As we'll see, wires can have dimensions, like an array, or which is a whole nother thing we'll talk about some other time with Verilog. The difference between an array and a multi-bit wire. Those are two different things. Bottom line is, there's a default, and if you don't declare what something is, it is assumed to be a 1-bit wire. And I found that 9 times out of 10, that's not what I want, and I'd rather get an error from the compiler. If you're just learning, don't be a fool. Okay? Shut off that kind of help. You don't want it. Learn how to do it right, and learn how to, be informed when you've forgotten something. Because, like I said, 9 times out of 10, I'm burned if I don't do this in an early draft while I'm debugging. Don't waste your time. Just shut it off. Okay, what do we got here? Verilog is made up of modules. As we'll see, modules are expressed in a hierarchical form. A module is a circuit, or a part of a circuit, or a part of would-be circuit, okay? And the way this works is you have a module, and when you run your program, what it really does is it has, it's instructed to run one and only one single module, which is referred to as the top-level module. Quite often that's called top. In this case, it's called TB. We'll talk more about my naming conventions of this some other time, but this is the one and only module we're going to be using for all these simulations today. We only have a single module program, which is uber trivial, just for the sole purpose of learning how to just make this thing go and control it, okay? Normally, however, what you'd have is a module, and then inside it you'd instantiate, we say, more modules and stuff like that, okay? We've already seen some of those, and I didn't go too much into the details of how all that works yet. We'll talk about it at a later time. Okay. What might be called variables, but don't do that. Call these signals, okay? I'll probably slip up a lot while recording these videos myself. They don't act like real variable. These are real circuit things, okay? 9 times out of 10, whether you say reg or wire, what you're creating is a wire, okay? A wire in a schematic, a net. If you think about it in like a schematic editor, you're going to get notes from the schematic, and so I'm going to create a net list, and sometimes it talks about a named net or a disconnected net and all that other stuff. When you run Verilog, it talks a lot about nets too. So these things quite often are nets. Sometimes these regs can be latches, in which case you can think of it like a register. But these are not automatically registers, okay? Honestly, this was one of my difficult things in early Verilog, to try and remember which is which, what's what, why. It's not really clear to me that at this point in time, maybe, in 1985, there was a reason for this. But today, it's not entirely clear as to why they don't just have one kind of signal. And when it needs to be a latch, it's a latch. When it's not, it's not. Or formally define what's a latch and formally define what's a net. Okay? Now, like I said, in the early days, maybe there was a reason for this. Today, it's different because, remember, Verilog was not designed to be directly compiled into an FPGA configuration and then executed in circuitry. It was designed to be simulated. So this, I suspect we're looking at a little bit of history here. This is easy to confuse. Don't, okay? The short of it is this. A wire is the only thing that can be driven outside of what we call a process, which is a lot of times called an initial or an always block, as you see up here. An initial and an always block can only assign values to a reg. Okay? So if you're going to create an initial block or an always block, we call a procedural block, a process in Verilog terminology, and you want to assign values to things, signals, those things have to be reg. If you're going to assign a value to something that's not part of a process, what we call a continuous assignment, or one of these, a structural circuit description. We'll talk about the difference between these two in a minute. Then you have to make the output, the thing on the left of the equals, the L value as it's often called, that thing has to be a wire. Okay? And assign, or a structural circuit definition, has to assign something to a wire. Okay? That's all there is to it. This L value has to be a wire. These things, because they're not in a process block, I should say, the first parameter is the output, and these other ones are the inputs. We'll see in a second here. This represents an actual XOR. If I want to, I can just create a whole bunch of these things and connect them all together with wires, and I can create a circuit that way. I will be, in text form, typing in a schematic, or quite frankly, just creating a net list. Okay? If you want to do it that way, you can. No one does it this way. Okay? Don't do it this way. That's the whole point of using Verilog, is to not have to go into this kind of minutia. This is actually a little bit easier. In this trivial case, these two are the exact same thing. However, quite often, you don't just simply want to calculate A ANDed with B. You'd like to do something like not A ANDed with B or C XORed with D. Quite often you want to do something like this. And this is much easier to read than, I suppose I should have typed this in so we can see it. What would that require? That would be a gate for this. These things represent single gates. Then there would be a gate for that. There would be a gate to AND these two things together, and there's a gate to XOR the blob on the left with the blob on the right. Okay, so there'd be many lines of these things. And then you'd have to look at each one of the variables inside here and make sure that the output of this thing, that might be, for example, the not A, right? So that would be, if you really wanted to do it, you'd write something that looks like this. Maybe XXXA. And then this XXX would have to be a wire, okay? A 1-bit wire, and then used maybe in another gate over here as one of its inputs. And this actually would work. You can create a 3-input AND gate by just adding more parameters. This, you can add as many as you want in here, okay? So anyway, I would argue that a morass of all these things and all the wires that connect them is harder to read. No one does this. This is the only time you'll see me do it, unless there's an incredibly rare situation. I'll use this form up here, okay? Especially when we get ugly and do it like that. And even worse, when there's complicated multi-bit values involved and things like that, all right? These are super trivial. You might say, who cares? Oh, you will, okay? So, anyway, if you see this in someone else's code, that's what's going on. That's the point here. For this first version, we'll run both when we actually run it. We'll see they're doing the same thing. We talked about this once before. Because we're simulating, we can actually write to files and stuff like that. And if we want, we can create this thing called a dump file, a value change dump, name it whatever we want. And we can, in this case, we're going to just dump everything that changes over the course of the time that the simulation runs will be dumped into that file. We'll talk more about this later when the amount of things that change over time become billions and overflow your hard drive. There's a way to say only dump this, only dump that. I don't want to see everything kind of a situation. But until you get that large, just dump it all. It's easier. Okay? Now, these initial blocks, and as we'll see later on, an always block, are what we call these procedural blocks. They represent what Verilog calls a process. All processes in the entire design start at the exact same time when the simulation begins running. Only if you put delays and what we'll see like sensitivity lists and things like that in your code will the simulation cause anything to wait for something to happen. Otherwise, it just barrels on through full speed. All these run all at the same time from the beginning of the simulation. Now, there are special things like the dump file where they guarantee that the dump file will be open before this assignment's done. In spite of what I told you earlier, where you might argue that maybe this could happen before the dump file is opened and so on, all right? Well, no. They cheat from time to time, and we'll see some more cheating as we go. There's very few cases where they cheat, and when they do, it's exactly what you wish they would have done, okay? And this is one of them. Make sure the file's open first. If this didn't work for you, you just simply remove this end and this begin and just put all this in one big initial process block so that this is done before that, by definition, okay? If we needed to do it that way, we would. But we don't, so this is cool. As far as I know. I look forward to your comments below. Anyway, I've always done it this way, and I've gotten away with it so far. Okay. These initial blocks, and as I mentioned earlier, there's an always block. These two are the exact same thing in all situations except for one thing. An initial block defines a process that runs once and only once, starting when the simulation begins. Okay? So this will run, and any other initials will run, and all always blocks will start running when the simulation starts. The difference between the initial and an always is that if this was an always block, whenever it gets done, it'll go back up to the top and immediately start running again. An always block is a loop, and an initial block is a do while false, right? It'll do it once and then stop right away, okay? Well, this is exactly what we want to do. If you just want something to happen in order one time, which is what you want to do in a simulation. The code we're going to see today here mostly runs in order, and you'll see that it doesn't do, and even though it runs in order, it's not necessarily what you always think it is. As I mentioned, you can have as many initial blocks as you want, and as many always blocks as you want. We'll see that down the road. Okay, the regular old assignment is what they call a blocking assignment, and I found this very confusing when I first started learning Verilog, and everyone on the planet acted as if everyone knows what the difference is between a blocking and a non-blocking assignment. They all give you different descriptions, and a lot of them tend to be some variation of parroting some random statement from some website somewhere, which when that happens, I argue not one of those people knows what they're talking about. If you look into the depths of the differences between blocking and non-blocking, I'll have a whole video on that, and we'll run through a bunch of scenarios down the road. on the one hand, they don't mean anything. They're not that different from each other because everything happens at the same time in real hardware anyway. And or they do matter, and a non-blocking assignment is closer to everything happening all at once, and a non-blocking assignment happens in the order that you see them right here. So if I say, for example, A equals 0, and then I said B equals A right here, and I guess we can do that in a second run of this simulation, you'll see that they're both set before we get down to printing them out, okay, or before we get to the next line here, okay? That's what a blocking assignment is. And this is more intuitive and closer to what you normally would think of if you wrote a regular C program or something, do this, then that, then that, then that, in order. And that's kind of what happens in an initial block. And I say kind of, but not always. So you got to be very careful because there are... Let's run this and then look more closely at it, okay? Now, as I say here, because no time has passed between assigning these and the time I'm going to run into this display statement, in a way, one might argue that these gates up here have not yet propagated their outputs through, okay? Now, in a simulation, that's not what it's simulating. It'll act like that. But that's not really what's happening here. What happens here is I've done things in this order in this process block, and they'll happen in that order, and they'll be in an intuitive way, because that's what this non-blocking assignment means to Verilog. However, if I got more than one of these initial blocks running at the same time, and they're both assigning things to the same values, these two things could intermingle in an unknown way and give you indeterminate results. What will also happen is I assigned A a 0 and a B a 0. Now, everything that happens in this initial block happens, and it will manifest the value, the L values of these signals will be expressed, like I said, that code, those two lines of code are the same as this in terms of the result that will come of this. However, the point in time, the simulated time that happens, is exactly the same time as this one here, and that's the same time as this one here, and so on. And it's not until I wait that the simulated time advances, okay? Now, in order to do a simulation like this, if you think about what must be happening when the simulator runs, what happens is there's these cues that it manages behind the scenes. Otherwise, how does it know what to do and when, right? So we've got these gates that we've declared up here, and they've got inputs, A and B, and they have an output. This one has a sum. This one has a carry. That's what these are. I'm going to create a half adder, right? Half adder is the XOR of two inputs is the sum, and the AND of the two bits represents a carry. That's how a half adder can be built, one way to do it, okay? Now, these gates have inputs in Verilog speak. We say it's sensitive to changes that occur on its inputs. Change events, in fact, it might be the correct Verilog way to say that. When this A and or B changes, an event is put into a queue that says, before you advance the clock, let anyone who has an A as an input know the input has changed so that it can do its job and calculate any output values that it might have. At which point in time, another event will put into a queue, in this case, saying that the sum signal has been modified, and here's its new value. And anybody who cares should now be updated. And that will create more events that go into this queue, and so on and so on. You must think in terms of these things going into queues, or you won't get it, okay? So here's what's happening. Assign 0 to A, then copy A into B. This will happen in this order because it's in one procedural block using a blocking assignment. These happen in this order. And they will complete before we get to here. And we will see that this display will print out A is 0 and B is 0. And it will print out garbage for sum and carry. Because what has happened is when A and B were updated here, 2 events were placed in a queue for the simulator to deal with later. And the simulator immediately proceeds on and does this. And because those other 2 events are sitting in a queue, nobody did the XOR and the AND operations yet. They will happen when all of the items in this procedural block are completely done and there's nothing else to do in this procedural block, because it either finishes or it has to wait until the future arrives. At which point here, those events will be taken out of the queue. These operations will be done. The sum and the carry will have been changed, and events will be posted in the queue again that says, take the outputs of these gates and put them into the signals where they go, which are right here. And then those events will be processed, because all of them are supposed to happen before the time advances. All right, all those are in the queue. It says, now, do this now, when you get around to it, okay? It gets around to flushing all that out, generating more events, flushing those out, and all that's done. It can advance the time, and then it can do this. So let's watch what happens with these first 2 display statements when we print stuff out. So you can recognize this. This will be a real big pain if you don't get this. Look what happens at time 0. There's my A0, B0. It does exactly as I said. Whether I say both of them is 0 or I set A is 0 and then I set B to A, as you saw in a blocking assignment, that will happen. But it says sum is X and carry is X. It turns out that in Verilog, all signals can have one of 4 states. Do I have that in this doc here? Maybe. Yes, I do. What happens is it can be a 0 or 1 like you and I expect. But remember, we're simulating in here. It's possible for the simulator to not yet know what the value is. And that's the case. I never gave it anything. It doesn't know what sum and carry are. Those wires have never been assigned any value. So it puts an X in there when I printed it out in binary. A Z is also another state. It is known to be floating. It's disconnected. It's on high impedance. Okay? So what we really have is a 4-state binary system. Quadrary. You might call them qubits, but that would be a whole mistake right there. Okay? They're quad bits. No. Okay? Each bit, even in a real circuit, it can be a 0 or 1, or it can be floating. And in theory, it could also be a value that you have no idea what it is, unless you go look at it or something, or wait, okay? So that's what's happening there. If you see X's and Z's coming out when you print out your variables, signals, I should say, I'm making mistakes already. That's what that means. And that's exactly what's happening right here. Do this, then do that, then print it out. Oh, wait, there's a queue of things that still remain to be seen that won't entirely be flushed out until we wait, all right? So this isn't too bad. It's annoying to have to do a bunch of stuff and then want to see it, and then you can't because half of it's not yet updated, and then have to wait and then print it out. It is a little bit annoying. But as you'll see in a real circuit, when you're dealing with state machines, they really do work that way anyway. So, let's just live with this, okay? If you want to know what something is, wait a little while, then print it out, okay? You can put some gratuitous delays in here, depending on how the rest of your system works. For now, we'll keep it real simple, and we'll put delays, then we'll print it out. We'll see some other ways around this problem if we want. So, the first display prints out, we saw X's for these guys, right? Then we waited. The second display comes out 10 nanoseconds later, and we see all the correct values. Now, I printed out, I printed out, and then I wait another 10 nano, then I change one of the bits, then I wait, and I display, and you can see here, change it, wait, display, change, wait, display, okay? And there's another example of it going too early. If we want to turn it on, you'll see that we'll do that in a minute. So let's look and see what's happening. So the first time it runs, we print. We saw that was too early. We wait, we print it again. So the first two prints basically are the same thing at different times. Okay. Then we change, print, change, print, change, print for the rest of the runs here. So if we look at the run, remember we're adding. So 0 plus 0 should be 0 with no carry. And that's exactly what we see 10 nanoseconds in. All right. 20 nanoseconds in, there was a double delay in there because we delayed after, then we made a change, then we assigned A and B again, then we delayed. So that's why this is up to 30 nanos in this particular case. And 0 plus 1 is 1 without a carry, so that's correct. Okay. Then we assign 1 and 0, which is also a sum of 1 of no carry. Then we assign both of them to be 1s, and that's a sum of 0 with a carry of 1. Okay? We then put them back to 0 again, just for fun, and we can see that that did the right thing. Now, it all printed out the right values because we always assigned it. We waited, because the simulation then finishes all those events that are queued up to deal with in the same, what they call that, in the same time period of the simulation. Now, notice what's happening up here, where we actually now, I mean, we solved one problem, but, this is still kind of confusing. Up here we said, what? Assign these things, display it right away. And that one said, I don't know what sum and carry are. Down here, if we did a similar sort of situation, we'll get a different wrong result. Okay, and I clearly marked this so we know. We'll run it again. And this time it's going to know what sum and carry are, but remember that event queue still exists. It's filled with events that say A and B has changed, but it's plodding along, and it does this before it goes back to its event queue of things that need to be taken care of sometime before the next delay. And it decides it's going to print this out right away. Therefore, the sum and the carry are going to have the stale values in them. So what happens? I got a 1 and a 0. Sum is 1, carry 0. I update A and B like you just saw, and then I print it out again. And I got the old sum and carry. This is just wrong. That's not 1 plus 1. It's not 1. It is 2, which is a 0 with a carry. Okay? So this is the number one thing I wanted you to take away from this particular video today. All right? Make sure you understand what's going on with these delays. Okay. Now, let's get back to that question there. So what happens? Okay, just so we're all aware of what's happening here. First one does this. We print it out. We got the X's. We wait. We print it out again. It's good. Now, we update it. We wait, and we display. So what if we don't wait more time here? Well, we don't, and we're getting this right result, in spite of the fact that, remember, no time in simulation passes between printing this out and doing this. So how come this doesn't interfere with this display? Okay? Well, these are all sequential blocking operations. And they blocking, they mean nothing else will be done until this one's done. Okay? It doesn't mean all the events will be flushed through all the queues. That means inside this process block, this display will happen before that happens, before this happens, before he starts waiting again. That's why this display happening at the exact same time as this is okay in the simulation. Okay? So if you were worried about it, you could do what we did up here. You could wait, display, wait again, and then do this. All right? And there might be times where that would be preferable. Okay? So the rest of these examples are all variations on this using different features that they give you to control time and how to display things. So let's look at this second one here. First of all, what are we trying to look at? Strobe. Okay, so the only difference between this one and then what we just looked at is I changed the word display to strobe. What happens with strobe is this plays games with that Q. All right? What strobe does is it says, I'm going to print this, but I'm not going to do it until I get to the point where the time would normally advance, which solves that annoying queuing problem. If all you want to do is see what all these values are in this particular simulated time step before the time advances, you can just say strobe, and it'll happen right at the beginning of this delay after all that stuff that I mentioned earlier is out of the queue. And this will actually print kind of what we had hoped, what I would, more intuitively. A is 0, B is 0. What is the sum right now? Because I've just made those changes. I can say strobe. And what we'll see here is it'll print what we might have expected the previous one to do, okay? And you can see all I do is I say assign strobe wait, assign strobe wait. So the big difference between the display was I said wait, and then I displayed down here, okay? And now I'm doing the A1, B0, and I do the strobe all at one time, in one time step, okay? So strobe automatically defers me. So the first one, you don't see X's anymore because it's at the end of the time step, not the end of the one element in the queue of events that are being processed, okay? When all the queue stuff that's all queued up, ready to go, that should be done is done, then this gets printed out. So the sum and carry will have been done, all right? Sim 3 uses, I believe, something called monitor. Yes, so there's another way to do it. All I do here is I say, oh, there's a little more to it. Okay, so the top of this is exactly the same as the other ones. This is I use the assign version, the what we call the behavioral model rather than the structural. I'll leave it as a task to the reader since we're running out of time already to run both of these and see that they accomplish the same thing. They definitely do. This thing called monitor, you can do one and only one of these in the entire system at any time, which I find weird. So what you can't just say I want to monitor the sum and I want to monitor the carry and stuff like that. What you have to do is you say I want to monitor, and then you just name everything you want all in one giant monitor. That's fine in a trivial thing like this, but as it gets more ugly and complicated, we might want to use different techniques. Now, the time, think about, okay, so what does a monitor really do? What a monitor does is it says every time A or B or sum or carry changes, I want to print this out. And what about this? This is handled especially by monitor because time is always changing. If monitor printed every time time changed, we'd have an infinite loop of spew, okay? So this is one of those weird special cases. So if you look up the formal definition of monitor, it is, if anything in here changes, it will print out all of these values, unless one of them is the time, okay? And again, that's an exception that, thank you very much. That's an appreciated one. So now we say monitor and monitor only once, and then we just do whatever we want. And we don't do any printing or displaying. We just simply say change values, wait, change, blah, 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 right? And now, because every time any of those variables that are being monitored changes, it fires off. And notice when this prints, this one prints at time 0, just like the strobe. When we did the display, we had to do it at the beginning of a following time delay, not in the same time as the changes that we've made. 0, 2, 3, 4, 5. It makes me think I got an extra delay in there. That's weird. What's going on in there? I thought I copied this code. I probably had 2 delays. Change 0, wait. Oh, yeah, there's a comment right here. Notice that no monitor will file here because nothing changed. Okay, I added this on purpose. A is 0 and B is 0, and I assign it 0 and 0. Okay, in this particular case, you might say, duh, but what if I had b equals some other variable like q in here? I don't know what q is, and q might even change sometimes. Sometimes it might be 0, sometimes it might be 1. And if q is 0 and this assignment is made, a monitor won't fire here, and it'll be missing. It'll be a lot like this otherwise laughably simplistic example. Okay? So if you're going to use monitor and your times are leaping forward in weird ways, make sure you understand what you're monitoring. Because if it doesn't change, monitor won't fire, even though an assignment has been made to it. Monitors changes, not assignments. That's a good quiz question if you were teaching this in school. All right, let's look at the README file on this one first. Okay, what happens if we delay 0 time? And how does the ternary operator work in Verilog? It turns out ternary works the same way as it does in C, C++, Java, and almost every other popular language. Okay, what do we got going on here? An explicit 0 delay. Okay, so this is right out of the spec, the Verilog spec. An explicit delay of 0 requires that the process be suspended and added as an inactive event for the current time so the process is resumed in the next simulation cycle in the current time. Blah, 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 blah. What the heck does that mean? Now you know why I threw in the discussion about these queues. What #0 does is it says do this, now. Put into the queue, with everything else in the queue, the need to resume execution of this in process right here. In other words, don't do this until everything else that is already pending and scheduled to finish in the same time period. In this case, it's this up here. These changes have already been posted as events in this giant queue. So somebody needs to process this assignment here and that one there. And I need to get around to that at some point when I'm simulating, please, thank you very much. If I say #0, what I'm doing is I'm throwing another event in that queue, so to speak, that says resume executing here. And then the simulation goes, okay, fine. I'll handle all the events that are in front of that. I'm at the end of the queue right now. So I'll take care of these other things. Okay, great. It does those things. It updates the sum and the carry. And that's all that would really be going on in this particular simple application. However, if assigning something, let's say I assigned this to carry, and then I used carry to go to some other variable and another one and so on, and this chained. That sequence of events will not necessarily play out before I resume here. That may depend on the kind of simulator you're running. That could be indeterminate. I'm at the back of the queue when I said this, but right now the queue only has 2 events in it to update A and B and to go and process these 2 assignments, okay? But like I said, if there's more that happen as a result of these assignments and that I do care about, then this will still not quite give me what I really want, okay? So I say be very careful if you're going to take advantage of #0. You need to understand what's in the queue now and what might be added to the queue by flushing the queue and that you still care about here. So I'll go back to saying surefire way to make, ensure that you can deal with things that have propagated through and been completed before proceeding is to wait for realsies. Okay? Because the simulation won't throw things in a queue and then not finish them if you actually have real time to waste in here, okay? Now, I say that with a huge pause because obviously if I put delays in here, then yeah, they would happen much further down the road, okay? So be careful how ugly and messed up your code gets with all these delays. And when I do test benches, when I use Verilog like this for non-synthesized code, I'm writing what we call a test bench. And it looks exactly like the sort of thing we're seeing here. I assign a bunch of values to signals that are used in something that I'm testing. And I don't test my test benches with test benches. I don't do this kind of thing with all these delays all over my code everywhere when I'm writing Verilog. It would get very ugly, very complicated, and kind of defeat the point of using this simulation code to test a synthesizable piece of code. Okay? And synthesizable code has delays as well, but they are not done like this. Okay? They're done in another way that you can also test. Okay, so sometimes you can get away with just putting a #0 in there in order to get your display to happen closer to the end, I should say, of the current time period. And in this particular case, because it's so simple, it will work fine. Okay? Now what about the question mark operator? What's up with that? What was I doing? Yes. You see where it says pass, fail? I forgot. We're going somewhere with all this, people. When we do this display, I'm going to end it with whether or not I agree that the result of the sum and the carry match what it's supposed to be. This is after all, I'm demonstrating how I test my code. So I'm going to write code to test the other code. So this is the first time we actually do something where we put what we'll see in a minute adds an assertion to our code. So if I set A is 0 and B is 0, and I print out all these values like this, it would be nice for me to also print out, because I might forget by tomorrow when I run this again, whether this is passing or failing this purpose of this test. So as long as the sum is 0 and the carry is 0 in this time, then I know the code that I am testing, namely the half adder above, did its job, because A is 0, B is 0, should be 0 for the sum and 0 with the carry. And I'll print pass. If that's not true, I'll say it failed. And that means that my code up here was broken. Okay? Now, every time I print it out, I do that. Now A is 0, B is 1. And now I say, if sum is 1 and carry is 0, then we're good. Otherwise, we fail. All right? Again, ternary operator, what this thing does is it evaluates this condition as if it was an if. If that expression is true, then it will say pass, and this pass is printed with this %s right there. Okay? If the condition is false, it'll print this, because this string will be printed where the %s is. That matches it there, all right? So every one of these is going to go through this. This one, sum is 1, carry 0. What do we got here? 1 plus 0 should be a sum of 1, carry of 0, all right? 1 plus 1 is 0 with a carry, okay? And 0, 0 again should be sum of 0, carry 0. So when we ran it, it said pass, 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 pass. So what am I really doing there? What am I really testing? Let's say I'm a dingus, and I forgot that the carry was the and I thought it was an or, and I blew it. Oh, no, heavens to Murgatroyds. So now we got, it works when I do this, but it doesn't work for these cases here. Fail, pass, fail, fail, fail. This is exactly what you want in a test bench. So, I found a bug in my code. I meant to say and in here. I knew that all along, right? Okay, now all of them pass. All right, so this is pretty useful. Let's look at the next one, because that's common for me. I like to have my tests test themselves, because you can also, as you've seen before, let's go back to number 4. It doesn't matter, because all these are just doing half adders. We can run the plotter, and sometimes people will say, just plot it and look. I don't want to plot it and look every time I make a change on a system that's got 1,000 modules. If I create an entire CPU, each one of the modules that we build, we might walk through and make sure, does that happen? Does that happen? Does that happen? Yeah, that's great. But every time I make a modification in my code, I'd rather just run a test bench and say, does it still match and give me the right results or not? And be done with it right there. Pass, fail, says on my screen. Otherwise, I got to open this up and remember what happened there. What was I trying to test? Is that supposed to be a 1 or a 0? I don't remember. Oh, no. This would take you months every time you change one thing. This is why a lot of people's code sucks. So write code that can be tested and verified by more code. That way, when you modify your code over the course of time, you can keep running your tests. As long as it's easy to test, I always submit programmers will test their code to death if it's easy. If it's hard, they'll never do it, and they'll hand out crap. Raise of hands, how many people say I'm wrong? Maybe one who's never written a line of code in your life? Put that hand down. I can smell it from here. Okay. So this one, what we're doing here is we're looking at macros. This is the define directive. Now, what we're doing is we're telling the compiler something, just like time scale and the default type, right? What we're doing here, if you've ever written a C program or a C++ program or creating a macro much the same way, they say pound define, we say backwards quote define. Why they didn't use pound, I don't know. I suppose it's because somehow confused it with that. I don't know. I can't stand it when people change things without a good reason. Anybody know the reason? Comments below. Honestly, I read all the comments in my videos. Whenever I ask for a comment, I'm serious. I want to know. Who knows why they did that? Okay, so my goal here is to get rid of the visual clutter. Look at this. Wouldn't that be nicer than having to print that massive display out every single time? And just like we were looking through there, and I'm like, is this a 1 or a 0? And I can't really tell because of all this noise of this giant format string and all the other crap going on in there. Penis in the bungus. All right? 0, 0, wait. Is that what I'm getting? Yes or no? Please. It should be that. If it's not, let me know. Change it to this. Wait. Is that what I got? Yes or no? A moron could follow this, okay? At least one of you is a moron, and you're following it, I'm sure. Just kidding. No one's a moron on my channel, except maybe me sometimes. Anyway, moving on. Okay, so what does this do? It defines a macro. Its name is assert. And if you want to use that macro, you have to say backtick assert. This here, just like in C, this token, this word in here, this identifier, is going to be substituted with whatever's in these parentheses. So in this particular case, all of that code will be replaced in here, in the body of the macro, wherever that word is seen. So look what's going on here. We got a display, a big string of stuff to display. We'll talk about some of this in a minute. And then we see a bunch of more stuff I'll talk about in a minute. And then you see conned, question mark, passed, or failed. And we see another conned over there. So what this means is when the compiler runs, sees this, says, okay, is there a macro anywhere called assert? Yes, there is. It's right here. What does assert need? It needs one item. One item is this. If there was a comma in here, that would be another token, all right? But this token here is this whole expression. That goes in for here. So what we're really doing is basically what we saw before. Print something with a string, a bunch of parameters, followed by asking if something is true. This is where this ends up, right there. If that's true, just say passed. If this is not true, it prints out assertion, and then it says, here's the assertion I was trying to match. Has failed. That's nice. If it says you screwed up, I'd like to know why. Because maybe this is wrong, okay? So what about the other junk in this display? It says a string, %0D. Now what's this zero crap? And when you say 0D and 0T when you're printing out the time, that says, don't help me with your foolish formatting. You can play around with this yourself, remove this number, and it'll turn out that it'll format the time as some gigantic thing, which is really annoying to me anyway. This number is, make it reserve this many digits or this many characters to print the thing you're going to print. 0 means print as least as possible instead of some gigantic thing. Thank you very much. Okay, so what are these two things printing? And this %m, what's this all about? Well, you've seen all this before. I've added a 0s there and a %s here. The parameters are double underscore, file double underscore, and then double underline, double under. These are macros, okay? And in Verilog, or at least in Verilator, this isn't Verilator, this is Icarus. Verilator is another kind of simulator. I'm sorry if I misspeak. When you run this through Icarus, file and line are replaced with the name of the file that this code came out of when it was compiled. And line is the line number where this code exists when the code is compiled. Okay? Time, we said before, is the current time from the simulator, and so on. Now, because this is a macro, file and line are not evaluated and assigned their values until the macro is used down here. So it turns out it will print out the name of the file, which I'm in Vim, so I hit Control-G, and it'll say toptb.v. And if we put the cursor down here, it'll tell me I'm on line number 34. Okay, it'll say toptb.v:34, and then it'll print out the time and all this other stuff and whether it passed or failed. So now I can see the assertion. If it fails, it tells me what the condition was. If I want to see the condition anyway, I could put cond over here too if I wanted to, and it'll tell me the file and line where that assertion existed. This is wonderful. All right? Honestly, I don't know how anyone writes code without this kind of crap going on. So, top TB line 34, time 10, A0, B0, the sum and carry are 0, and my assertion has passed. This is how I like to test my code. Now, this doesn't always work. It's not always perfect because of all this crazy timing and the queues and all this other fun stuff. So these, again, I wanted to give you a bunch of a variation of ideas here that some situations they'll work. Some of them they might not. You might have to tweak them, or maybe use a hybrid of a multiple of these. But my favorite is to minimize the noise in the code that matters. Even if it caused great expense to me elsewhere, I set up this one macro once, and now I can easily understand what's going on down here. Okay? Now, I've noticed while teaching, even in the college level, a lot of students tend to ignore warnings and messages when they run programs. So, let's move on to the next idea. What does my readme in here say? Multi-line macros with an if conditional. This is the final version of the macro that I would use for this particular test case. Now, instead of assert and just dumping this thing out, what I'm going to do is I'm going to say I want to assert that this condition is what? If the condition is false in this case, I'm going to print out this message right here that says assertion failed, and I'm going to print the condition. And I'm going to stop the simulation. And if the assertion is true, I'm not going to say anything at all. This will act a bit more like how they work if you put it in a C program. Causes the program, in this case the simulation, to halt. Okay? Now, if that is running, and I still want to see things to change over the course of time, I can also put a monitor in there. So I can monitor all the variables I want. I can include these assertions, and the assertions will shut up unless there's a problem. And this, like I said, mixture of multiple things might work well for us here, okay? So in this run here, as it is, what I'm going to do is I'm going to run it. This has the monitor going. The monitor prints the time and all this fun stuff. Now, the problem with the monitor is, by the way, I can't print the file and the line number. Because if I print file in line, it'll print me the line where the monitor is. It won't print down here where they change. It won't tell me where the code was when it changed. So there's a negative for the monitor. Okay? Positive for the assertion, because I can use it there, because the macro expands that way. I could write a macro that expands into a monitor. No, it want that. No, I can't. That won't work either. Okay? So this will be a disastrous mess. If you want to see file and line number, you're going to have to use some kind of strobe or a display or something like that. Okay, so if I take the monitor off and I run that, what happens is it says nothing at all if it succeeds, and if it fails, let's break it. What do we got? And, or, XOR. Oh no, it failed on line 47 because I wanted sum to be 1 and carry to be 0. And I did not print out the other thing. Maybe I should have printed A and B out. I'll leave that as a test to the viewer to add more stuff to be printed out in that macro. You might add more parameters in here, in which case you can add more tokens to the parameter list in the macro, and you can go nuts with this sort of thing, all right? So this is what I mean when I say, it depends on what you want to accomplish, how much you want to see, how you want to see it when you're testing your code. When you finally get your code to work, is when, in my opinion, you shut off all the noise, you leave the assertions all in there, and when you run your program, you should see totally no output at all, unless there's a failure, and it'll simply print out that there's an assertion. And the reason I leave my programs in that stage is because I believe they've already been debugged and they become part of a bigger system. And I don't want to see noise when I run all my test benches after I've made modifications. So it's hard to do this while talking. I made a modification, I fixed it, and then broke something. Thank God we have a version control. So what have I got? I got the wrong thing in there. Put this back to an and. This is what I have checked into the repo. My point is, when I'm totally done, I usually would leave it like this. So when it runs, no output is a good sign. Silent success and noisy failures, okay? And that way, when I'm done with the project, I might have a whole bunch of modules, and to test it, I might run, 20 test benches, and I want them all to run, but I don't want to see spew all over for each one, okay? And that's what I'm getting at. Does this make sense? Do you see where we're going? So the big takeaway here was, make sure you understand that there's this idea of this event queue, that changes are queued up for the simulator to process down the road. And in a way, that is analogous to what happens with propagation delays in real circuits. So that's not the worst thing, okay? But that's literally not what's happening, so don't confuse the two. Hopefully we got something out of this, and maybe you can tinker around with these examples and try things and break stuff and then learn by fixing what you broke. Anyway, thanks for watching. I'll see you next time.